Hi, I'm Adam.
And I'm Todd.
This is the Machine Tech video blog, and today we're going to show you how to case harden steel. One of the most common projects for machinist apprentices and students is to make these 1-2-3 setup blocks, which machinists use for practically everything in the shop. They're rough machined and then surface ground to precision parallelism, perpendicularity, and flatness of the surfaces. Since they're going to be used as tools, it's common to heat treat them to harden them so that they're more wear resistant. But the problem is that these are made out of 1018 steel, which is a low carbon grade. It's a good general purpose steel, but it doesn't have enough carbon content to really heat treat and harden properly in the furnace. The solution, of course, is to add more carbon. Lay down about an inch of carbonaceous material in a steel box with a tight-fitting lid. Yes, we really are using broken up charcoal briquettes because it actually works pretty well. Arrange the blocks so that they're not touching each other or the box. Go ahead and put in 1 or 2 pieces of 1018 steel scrap so we can test the hardness later without putting divots in the finished parts. Then pour enough carbon on top of the blocks to cover them by at least 1 inch. Put the lid on top of the box and fill in any gaps with fire clay or refractory mortar to form an airtight seal. The mortar should ideally be a little thicker than this. The method we're using to add carbon to steel is called pack carburizing. Pack carburizing is only one of several ways to add carbon to steel, and it's the slowest and most labor-intensive method. For this reason, it's not really a viable commercial process anymore, but it is used frequently in small shops. Now it's time to load the box into the cold furnace. We'll leave the box in the furnace to carburize for 8 hours. Since we've got some time to kill, let's measure the hardness of a piece of untreated 1018 steel using a Rockwell hardness tester. The test is simple. An indentation is made in the material using a diamond tip and a calibrated force. The size of the indentation determines the material's hardness. The diamond tip will penetrate deeper into the surface of softer materials than harder materials. A higher number on the Rockwell C scale indicates a harder material, with the scale topping out at 100. Our untreated piece of 1018 steel comes out to 10 Rockwell C, which is really not very hard at all. But inside the furnace, there's a bit of science magic happening. Carbon-rich gas comes in contact with the metal surface, breaks down, and some amount of free carbon is dissolved into the hot steel. Time, temperature, and the composition of the atmosphere all affect the rate at which carbon is absorbed and how deeply it penetrates into the steel. After 8 hours at 1700 degrees, the carbon should penetrate 1/16 of an inch into the part. After letting the parts cool in the furnace overnight, it's time to take them out. Remove the carburized parts. They're still soft right now, but the finished parts will have a tough, low-carbon core and a hardened, high-carbon surface layer called a case. This is because the carbon only dissolved to a certain depth, so the hardening process will only affect the outsides of the parts. That's what makes this process case hardening, as opposed to through hardening. Turn the heat up to 1450 degrees Fahrenheit, and then put the parts back into the furnace. We only need to get the parts up to temperature, so 10 to 15 minutes should do the trick. At room temperature, the microscopic structure of the high-carbon steel is composed of alternating layers of iron and brittle iron carbide. This microstructure is known as perlite. When the steel gets hot enough, the perlite dissolves and the microstructure transforms into a non-magnetic solution of carbon and iron called austenite. Once all of the perlite is dissolved, it's time to quench. Pull the parts out with a set of tongs. Quickly plunge them into a container of water and agitate the parts in a figure-8 motion until they're cool to the touch. Because we're cooling the steel so rapidly, the austenite won't have enough time to separate back out into iron and iron carbide. The resulting steel microstructure, called martensite, is composed of needle-like shards of iron supersaturated with carbon. Martensite is very hard stuff indeed. But the harsh process of quenching leaves a lot of internal stresses in the steel. And that's why it's common to stress relieve quenched parts by heating them back up to a relatively low temperature and holding them at that point for some amount of time. So let's go ahead and heat up the draw furnace to 400 degrees Fahrenheit. Place the parts in the basket and lower them down into the furnace. Make sure to replace the lid. By the way, this part of the process is called tempering or drawing. One hour should be plenty of time. Remove the parts and let them air cool at room temperature. Don't go dunking them in water at this point. It's normal to lose a little bit of hardness during the tempering process, but these parts are ready to be finished machined on the surface grinder.
So that's the basic procedure for case hardening low-carbon steel.
And that's it for today from the Machine Tech video blog. I hope you learned something.